Hello, this is section 7.9. In 7.9, we are going to be dealing with unimolecular reactions. We're going to cover a lot of ground here about SN1 and E1, and by the end, you should all be experts in the ramifications of all things two-step unimolecular reactions. So let's start by considering the following reaction that takes place in a solvent that discourages SN2 and does not have a base strong enough for E2. We're going to run this reaction in ethanol, and what we're going to see, unfortunately, is that we get a mixture of two products, mainly that the SN1 and E1 are both in competition. And let's remember that the reaction rate is going to be more or less constant for this reaction, no matter how long or how much we change the reaction, because the rate law is totally dependent only on the alkyl halide. It is the reason why we call these SN1 and SN1 and E1 is because the rate law is first order in that there is only one exponent here, this implicit 1 with the alkyl halide. Right, so if we look at the SN1 mechanism and the E1 mechanism, which we'll cover in a second, you'll see some similarities. The SN1 mechanism, again, just as a review, starts with the leaving group leaving to make a carbocation. Then you have attack by the solvent in this case, which is ethanol. But when the ethanol attacks, you have a positively charged oxonium ion here that is only relieved whenever you have another base, in this case the solvent, again, because there's so much of it around, taking that hydrogen to give you the neutral ethyl ether here, as well as the protonated solvent. And each of these actually are in equilibrium, so we're going to give that guy equilibrium there, and just make sure that we write in our solvent here being protonated so that we don't forget. There we go. There we go. It's a weird solvent, but here we are. Okay, now in E1 reaction mechanisms, you might see that things are pretty similar in that the leaving group leaves first and the carbocation is generated. But this time, instead of the solvent attacking, you actually have the solvent acting as a base and taking one of the protons to eliminate into the formation of a double bond. And doing that, you again get your protonated solvent to make the E1 product. And it's important to note here that the E1 product is preferred if the alkene is tri or tetra substituted. So anytime you have them and they have this option of reaction, for this specific example, the E1 reaction here would be preferred, making this product the major product that we see. All right, so now we're back up to speed on SN1 and E1 reactions. So let's talk a little bit about something that makes these reactions very special, and that is the possibility of having rearrangements occur. And if you remember, rearrangements are one of the foundational mechanism types that we have in organic chemistry from Chapter 6. And there are going to be two main types of reactions that we talk, or rearrangements that we talk about, the hydrogen shift and the methyl shift. So let's first talk about the hydrogen shift, or the hydride shift, if you will. So let's take this reaction. This blue alkyl halide, if you react it in water with heat, the Greek symbol capital D, delta, means heat generally in organic chemistry. So if you run this reaction in water with enough heat, what you'll find is your product mixture will contain both the substitution E1 product and the weird substitution, the substitution SN1 product that we expect, plus another product that appears to be an SN1 substitution product, and of course some E1 products as well. But we're not going to worry about the E1 products at the moment. We're going to focus just on the two SN1 products that come up. And the reason why you have two is shown or is more clear if we draw out the mechanism for this reaction. And it follows the basic scheme in that you have a leaving group leave first to make your carbocation. But you can have a hydride shift from the tertiary carbon here to this secondary carbon, which makes a tertiary carbocation, which is much more stable than the secondary carbocation. Once you have the stable carbocation formed, then water will attack, making a hydronium ion, which then is relieved whenever another water, which is a solvent, comes and takes the proton to make the alcohol that we expect here, or sorry, the alcohol that we don't expect here, and the protonated water solvent. Now, of course, to get the product we expect, instead of having the hydride shift, you can just have water attack to make the hydronium ion or oxonium ion here, and then have water take this proton acting as a base to generate your alcohol and your protonated water. As I said, instead of a hydride shift, you can actually have a methyl shift, which has more or less the same mechanism, and which, as you can see here, whenever you heat up this alkyl halide with water in the presence of enough energy, you can have, again, the molecule you expect or a molecule that you maybe didn't expect. And that, again, is due to the methyl shift. And the mechanism is the same, basically, except instead of a hydride shifting, as was the case up here, you now instead have an entire CH3 group shifting over to give you the tertiary carbocation. And one interesting thing about this rearrangement idea is that there are some very key reactions that don't happen because of the rearrangement, such as this one. If you're hoping to do a substitution on this carbon by heating up this alkyl halide in water, you will not generate this product. In fact, it's not observed. The only product you'll see is this one that appears like it maybe could be due to a carbon shift rearrangement. And the question is, why would that be? Well, if you do the first step to try to make the primary carbocation, that's not going to happen because primary carbocations are not stable. Anytime that you might generate a primary carbocation, don't do that instead. You should never generate a primary carbocation in your reactions because they are not stable at all. Instead, what you should do is, in this case, something that looks very weird. You should, what happens in this reaction is that the methyl shift happens before the leaving group leaves. And it only happens this way because the primary carbocation is so unstable. And so the methyl group shifts, kicking out the bromide anion, making this tertiary carbocation. So now that we've seen kind of what rearrangements can do in SN1 and E1 reactions, why don't we have a look at solvent effects on these reactions? So if you run this reaction here, this 2-chloro-2-methyl propane in a solvent to generate the carbocation and chlorine and chloride anion, you'll see a very big difference in the reaction rate based on the solvent. Remember, we're studying this key intermediate step here, the generation of the carbocation, because this is the rate determining step for the rate law. This is the slowest step in the reaction diagram we learned about several sections back. So if you look at the solvent and the reaction rate, and you only look at the solvent based on how polar it is, larger dielectric constant numbers mean that the solvent is more polar. And if we take water to be our standard solvent, we'll see that as you lower the dielectric constant of the solvent, meaning as you make the solvent less polar, the reaction rate slows down. From water to methanol even, it decreases by a factor of 8 times slower. And in ethanol, it's 40 times slower. That's huge. So the take-home message here is that more polar solvents make for a much higher reaction rate. So we know how solvent affects SN1 and E1 reaction rate, but what about substrate effects? What about the molecules themselves affects the reaction rate? So if we look at substrate effects, let's first look at the leaving group. So if we compare these halide anions and we try to find out how their identity affects the reaction rate, what we find is that the reaction rate increases drastically going from left to right here. As you go down the periodic table here, they increase huge. The increase is huge in the rate because as you go down, these become better leaving groups. Bromide and iodide, even though they are less, they are more stable conjugate bases, they are better leaving groups, and it's actually for that reason. Similarly, we were talking about how rearrangements happen because carbocations are more stable. And in fact, if you change the identity of the carbocation, as we were talking about in Chapter 6, the stability also increases. So as you increase the stability of the carbocation, the reaction rate also increases pretty dramatically. And the take-home message here is that the reason why you have a higher reaction rate is either because of better leaving group or a more stable carbocation, as long as you keep the solvent the same. Now, let's look at some regio and stereochemical outcomes for SN1 and SN2 reactions. So a regiochemical outcome, if you remember, could be something like this, where you heat up this alkyl chloride in water, and what you'll find is that you can actually select between the external Hofmann product and the internal Zaitsev product fairly easily. And that's because the internal product is much more stable than the external. And the carbocation is much happier to be there than on the external part. A stereochemical outcome here could be as shown here, where let's say you have this chiral alkyl bromide. The bromide leaves, giving you a carbocation shown here. Now you have a planar carbocation, and there is both a front face, kind of in front of the carbocation, we could say, and a back face on the back side of the carbocation. A nucleophile could attack from either side, giving you the blue one or the red one as shown here. And you would think that each of them have potentially equal chance to happen. And that's mostly true. If you do this reaction, you'll get almost 50-50 of each product. But it's not totally 50-50. And the reason why is because as the bromide is leaving, it has a negative charge and it is leaving a positively charged molecule. Well, that's not going to happen very quickly just due to electrostatic interactions. That's just physics. So the negatively charged bromine on one side is actually going to fend off for just a little bit any of the nucleophiles coming to attack from this side. So there'll be a slight enrichment of isomers that were due to nucleophiles attacking from the backside. Okay, and that is section 7.9, which was unimolecular reactions. We've covered a lot of ground, and I hope that you found this lecture useful.